Okay, so let's look at Unit 11, Acids and Bases and Salts. So you're very familiar with acids and bases. They're important in health, industry, environment. Some of the acids that you might be familiar with, you can read them here. Citric acid, which is in lemons, limes, and grapefruits, or ascorbic acid, which is vitamin C. Acetic acid is the acid in vinegar. Hydrochloric acid in your stomach. Aspirin is acetylsalicylic acid. And then soda has carbon dioxide dissolved in it, is carbonic acid. Some of the common bases that you're familiar with are calcium carbonate or magnesium hydroxide, which are in antacids. Lye is sodium hydroxide. It's often found in drain cleaners, oven cleaners, and used to make soap. Ammonia and bleach are both bases, and baking soda, which is sodium bicarbonate, is also a base. So here's just some pictures of some of the acids and bases that you're familiar with. All right, so let's talk about the definition. What is an acid? What is a base? Well, Arrhenius was someone who studied acids and bases in the 1800s, and he described an acid as any substance that produces a hydrogen ion, an H+ ion, when dissolved in water. So nitric acid, HNO3, when it dissolves in water, breaks apart into the nitrate ion and the H+ ion, the hydrogen ion. A base, then, is any substance that produces a hydroxide ion when dissolved in water. So an example, potassium hydroxide breaks up into K+ and OH negative. Just a little note you can see on the bottom, when you talk about an H+ ion, think about it. A hydrogen has one proton and one electron, and if it loses its electron to become positive, all it really is a proton. And so often you will hear me use the word proton when we're dealing with acids and bases, and in that case, whenever I say proton in terms of acids and bases, think of H+. And so an H+ ion can interchangeably be called a proton. So you may hear me use either term throughout the rest of this lecture. All right, so there are some drawbacks to the Arrhenius theory. The first, as you can see, is that they really only describe aqueous solutions, which has to do with water. So you can't talk about acids and bases in other solutions. Acids and bases may not be evident by looking at their structure. And also, technically speaking, hydrogen ions can't exist alone. What they do is they sort of glom onto an H2O molecule to become H3O+, which we call the hydronium ion. So, and also another note, often we'll talk about H+ or H3O+ or the hydronium ion, and just also keep in mind that throughout this talk, these two terms can be used interchangeably. So technically speaking, H+ is what we're talking about, but it's usually glommed onto an H2O water molecule, and so it's the hydronium ion, H3O+. In fact, lots of times a bunch of water molecules with the H+ will join together, and so it's actually not even one. But so if I say H3O+, I also mean H+, and vice versa. All right, so the more advanced definition of acids and bases is the Bronsted-Lowry theory. These were two scientists in the 1920s who independently studied acids and bases, and they extended the definition. Okay, so according to their definitions, an acid is any substance that can donate a proton, a hydrogen ion, of course. Or you might say it can give away a proton. It can donate a proton to someone else, or it has something it can give away an H+ ion. Therefore, a base is any substance that will accept a proton from another substance. So it can accept an H+. And so in this case, whenever we have an acid-base reaction, there's always a transfer of a proton, transfer of an H+. So the acid will give it away, the base will accept it, and in that process we have a reaction. So if you look at the reaction below, HNO2 is an acid because it has an H to give away. Now, acids and bases in their reactions come to an equilibrium. So as we talked about back in Unit 10, or I'm sorry, Unit 8, in equilibrium. So notice that the arrows can go back and forth both ways. So if we look from right to left, NO2 minus plus H3O plus to give H2O and HNO2 in the backwards direction, we can also notice that we have an acid-base proton transfer. So in this case, H3O plus is an acid. It can donate a H plus to the NO2 negative, which is a base, and then it can produce H2O and HNO2. So either way, when you look in either direction, we have a proton transfer. So if we're going left to right, the HNO2 gives a proton to H2O. If we're going from right to left, the H3O plus gives a proton to NO2 negative. In a little while, we'll talk about which way is more likely to happen and how that works. But for right now, just notice that you can go either way. All right, so you might now be able to see the connection between HNO2 and NO2 negative. So they only differ by an H plus. H2O and H3O plus only differ by an H plus. So if you talk about these as pairs, we call them conjugates. They are conjugate pairs or conjugates of each other. So HNO2 is an acid and NO2 negative is the conjugate base. H2O is the base and H3O plus is the conjugate acid. They're conjugates of each other. And they're always linked. They're only differ by an H plus. All right, so again, conjugate acid-base pairs are any pairs of molecules or ions that can be converted to the other by a transfer of an H plus. So any acid, so as we just saw, HNO2, has a conjugate base, NO2 negative, and any Bronsted base has a conjugate acid. So how can we predict what the other one is? Well, if you have a base and you want to find the conjugate acid, you add an H plus. The way to do this is to increase the number of H's by 1 and then increase the charge by 1. So let's look at the example. Cl negative is the base. To find the acid, we add an H to give us HCl, and we increase the charge by 1. So it goes from a -1 to a 0 charge. H2O, we increase the number of H's by 1, H3, and then the charge increases from 0 to +1. NH3, we add an H, NH4 plus, and we increase the charge by 1, so that's where the plus comes from. HPO3 is a -2. If we increase the number of H's, it becomes H2PO3, and then if we increase the charge, it goes from -2 to -1. Notice that for the most part, the H's go in the front of the molecule. The really only one exception that we'll be dealing with is the NH3. And so it kind of something just to keep your eye out for. NH4 will lose one of those H's, but no more than that. And they're the exception where the H goes on the end. The other ones will go on the front. All right, if you're trying to find the conjugate base from the acid, then we remove an H plus. To do this, we have to decrease the number of H's by 1 and then decrease the charge by 1. So if you have HCl, it becomes Cl negative, goes from a 0 charge to a -1 charge. H2O becomes OH negative. We remove an H and it becomes a negative charge. Note this is the other exception. Once you take away one of the H's for some odd reason, we write it as OH negative rather than HO negative. If you forget and write HO negative, I won't count that wrong or anything. It's no problem. H2SO4, we lose an H, becomes HSO4. We decrease the charge by 1. So if it's 0, it goes down to -1. NH4, we lose one of the H's, it becomes NH3. Now NH4 is a positive one, and so if we decrease the charge by 1, it becomes neutral or 0. HSO4 negative, if we remove an H, we get SO4, and if we decrease the charge by 1, we get -2. Sometimes students forget the 0, so if you want to decrease from +1, you go down to 0, and then if you go from 0 decrease down to -1, -1 decreases to -2. And the same thing happens in the other way. If you're at a -1 and you increase the charge, it goes to 0. If you're at a 0, it goes up to +1. Okay, so if we're looking at this example, find the conjugate pairs of the following equation. So what we're looking for are two molecules or ions that are connected, that are the same except for an H+. So if we look at the NH3 and then we look over on the right, we see NH4+ and OH negative. So we can see that NH3 has been changed to NH4+. It has NH3 is the base and NH4+ is the conjugate acid because we've added an H+. And then if we look at H2O and we look on the right hand side, we see that that has become OH negative. So NH3 and NH4+ are conjugates of each other. H2O and OH negative are conjugates of each other. In the second example, C2H3O2, which is acetic acid, becomes C2H3O2 negative. It's just lost an H+. And then H2O has become H3O+. So those are conjugates of each other. So there you can see it. And of course, the base is the thing that gains the H, and an acid is the thing that loses the OH, that donates an OH. I'm sorry, an H. All right, and the nice thing about the Bronsted-Lowry reactions is that they don't have to involve water. So you don't have to always be looking for water. So in this case, HCl becomes Cl negative, so that's clearly HCl is the acid, Cl negative is the base, and then NH3 is the base, and NH4+ is the acid. So in this case, HCl has donated a H+ to NH3 to get those products. Okay, so here are some things to consider. Acids can be positive, neutral, or negative as long as there is an H to give up. So H3O positive, H2CO3 is neutral, H2PO4 negative is negative, and they all have H's that they can give up. NH4 positive is also an acid. Bases won't ever be positive, but they can be negative or neutral. So here's some examples. Cl negative, OH negative, NH3. Another example would be CO2 -2. That can be a base. So it could also be a -2 charge or a -3 charge, as long as it won't be positive. And then you can see that some acids can give up more than one H+ ion. So if an acid like HCl only has one H to give up, as we can see in this case, we call that monoprotic. Protic comes from proton, so there's one proton, one H+ that it can give up. Carbonic acid, which is H2CO3, as you can see, can give up two protons. We call that diprotic. So you can see in the first equation, H2CO3 becomes HCO3 negative. It gives up one H. And then in the second equation, it gives up another H to become CO3 -2. And then even we can have triprotic. The only one really that we'll be dealing with is phosphoric acid, H3PO4. But as you can see in the first step, it gives up one H to become H2PO4 negative. That can give up another proton to become HPO4 -2. And then HPO4 -2 can give up one more hydrogen to become PO4 -3. All right, a couple of other things. As we've seen, some species can act as either an acid or a base. And we call these amphoteric compounds. They can go both ways. So we saw before that H2O can gain an H+ to become H3O+. So in this case, H2O is a base and H3O+ is the conjugate acid. But H2O can also lose a hydrogen. H2O can become OH negative by losing a hydrogen. ion. And so in this case, H2O is the acid and OH negative is the base. Another example is HCO3 negative. So it can gain a hydrogen to become H2CO3. And so HCO3 negative is a base that is accepting the H plus, or HCO3 can be an acid and it can donate the H away to become CO3 negative 2. So again, and there's others out there like the PO4s. If something's diprotic or triprotic, they can give up usually more than one. Then the middle charged ones can go either way. And then also, a substance cannot be a Bronsted acid unless it has an H to give up, but I just want you to realize that not all H's are acidic. And at least this might not always be true, but at least in this class, any acidic H's are usually written first. And so that's why you can see, like with C2H3O2, that's why we write the H's differently, because the one H is acidic and can be given away, but the other H's are actually not attached in a way to be acidic, and so they cannot be given away. So that's why we separate them. So HC2H3O2, which is acetic acid, is only monoprotic. It can only give away one H. And so you can get in the habit of writing the H's in the front, and I will always put the acidic H's in the front. The only exception to that is the NH4+. NH4+ has only one H plus that it can give away. It can't give away anymore, and it's written included in the NH3s, added into there. So you just need to remember that exception. HC6H5O, which is phenol, has an H. The first H is acidic, whereas those other 5 H's are not. So again, we keep them separate. Now in H2SO4, since I've written both H's in the front, then they're both acidic. So let's just talk a little bit about naming acids. A binary acid is just an acid where you've got one element along with the hydrogen. So these are some examples of binary acids. HCl, when we learned in the naming system before, was hydrogen chloride, or HF was hydrogen fluoride. Now, when they become acids, what that means is they're dissolved in water, and so the name gets changed. You can see that the IDE ending gets changed to ic acid, and we add hydro in front of it, so HCl becomes hydrochloric acid, HF is hydrofluoric acid, HI is hydroiodic acid, hydrobromic acid, and hydrosulfuric acid. So you don't need to remember the rules about them, but just remember these acids. So binary just means with one element with a hydrogen. There are also oxo acids, which means that you've got an element plus oxygen plus some hydrogen ions. When the oxo acids dissolve, they usually produce the H plus ion and then the polyatomic ion. So these are actually where the polyatomic ions come from. They're groups of atoms that together are an ion, and when they form H with H plus, they become acids. Now, this is a little bit more of a complicated naming system, and again, I don't want you to remember the naming system, but here's where it comes from. If the polyatomic ion ends with the ATE ending, it gets replaced by the ic acid. So you can see the examples on the left. HNO3 is nitric acid. When it loses its H plus, it becomes the nitrate ion. Sulfuric acid comes from sulfate. Carbonic acid comes from the carbonate ion. Phosphoric acid from the phosphate ion. Acetic acid comes from the acetate ion, and the chloric acid comes from the chlorite ion. Now, those are the main ones that I want you to know. Some of the polyatomics, if you remember, I didn't tell you that you needed to remember them. The ones that end with the ITE ending, they get changed to OUS or US acid. So for example, NO2 negative was the nitrite ion, and so when it forms an acid, it becomes nitrous acid. And same thing with SO3 negative 2 was the sulfite ion, and so when it becomes an acid, it is sulfurous acid rather than sulfuric acid. And notice that oftentimes the us acids are one fewer oxygen than the ick acids. Again, I don't really care if you know the us acids so much, so just the examples on the left that I've shown you. But there's one other acid that you should know, and that's the HClO4 or perchloric acid. Okay, and then finally, naming bases. They're really easy because most of the bases that we'll be dealing with are the hydroxide ions combined with group 1A or 2A metals, and they're just named the way that we've already learned how to name them. So NaOH is sodium hydroxide, KOH is potassium hydroxide, lithium hydroxide, calcium hydroxide, etc. One other base that you should remember is NH3, which is ammonia. All right, so before we end this little section, let's talk about the properties of acids. Most acids have these certain properties in common. They usually taste sour. You can think about, like your citric acid or lemons, of course, all of those are sour. They will produce H3O plus ions when dissolved in water. They change the color of litmus paper. Litmus paper is an indicator, and maybe you might look it up online or something, but it will turn from blue to red. If you start with blue, it'll turn red. They react very violently with metals. So here's an example. Magnesium metal will react with HCl, and one of the products will be hydrogen gas. It will bubble up. You might look up that reaction online too. Maybe I'll try to find it for you. Let's see, acids also react with metal hydroxides to form salt and water. This is called a neutralization reaction. So basically an acid reacts with a base to give us a salt and water. And then also acids can react with carbonates, CO3 negative 2, which is a base, to give off carbon dioxide as a product. So what happens is the HCl donates the H pluses to the CO3 negative 2 to give us H2CO3, and then that breaks apart into H2O and CO2. And you can think baking soda and vinegar. If you put sodium carbonate in vinegar, like baking soda in vinegar, this is what you'll get, CO2 bubbles. Bases have different properties from acids, and they all have very similar properties to each other. So they tend to feel soapy or slippery. Soaps, in fact, are made out of lye, or at least the original soaps were, and so they're slippery. If you taste them, they taste bitter. So you've kind of probably, if you've ever tasted soap, you know what that means. They will produce OH negative ions when dissolved in water. They will take litmus paper and turn it from red to blue. They will react with acids to form a salt and water, so like the reverse of the last slide, their neutralization reaction. And also bases will react with fats and oils to convert them to soap. So they form glycerol and a crude soap.